Hello. So in this session, we'll be discussing our last portion in the RCC part that was pending. We already discussed the design of beams, design of columns, design of slabs, and now we'll be looking upon design of footing. And in that case, we'll be looking upon design of isolated footing in this case. So basically, isolated footing is divided into three parts that we'll be looking upon that you already seen in the previous semesters, and then we'll be designing in the portion that is for our section. And keep in mind, this question is asked in G2 examination for 7 marker, for 10 marker, and for 14 markers. So 14 markers question also can be asked from this portion or this chapter 4. So keep in mind, solve it accordingly. And it is an important sum regarding our G2 examination is concerned. So moving to today's question, the question here is design an isolated square footing for a square column having the dimension 400 mm cross 400 mm. These are the dimensions of the column that is being resting on the foundation that is to be designed, and it carries an axial load of 800 kN. Keep in mind, it is only mentioned axial load, that is not mentioned the word that is it is a design load or a factored load, so we always need to multiply it by 1.5. Use concrete grade M20 and Fe 250 steel. Keep in mind here Fe 415 steel is not given, so mild steel sections are used for this construction. And the SBC of soil, that is soil bearing capacity, is given as 120 kilonewton per meter square, and it is given that provide all necessary checks. If it is given in the question that we need to check or provide all necessary checks, then and then only we will be dealing with each and every check. Else it will be specified in the question that you need to focus on the specific checks. Clear? So checks will be done by you only if it is asked in the question. If it is not asked in the question, then there is no need to provide checks for it. So the first thing that we'll be looking upon is how many isolated sections are being classified. So our foundation, our isolated foundation will be divided into three parts. The first one is the pad footing that we'll be designing now. Second is step footing that is not asked in our examination, and the third is slope footing, which is similar to pad footing, just angles will be included in that. So we'll be discussing this portion that is our pad footing. So here the size of footing. So first thing we'll be designing is the size of footing, and keep in mind for footings we always need to assume that whether it will be under steel loads or in the under RCC loads, you always need to assume that the 10% of the total load will be included as the self weight of section or the 10% of working load. So as it is already given in the question the load to be working load, we won't be firstly multiplying by 1.5, you will be using the same load, that is the working load, and then we'll be taking the 10% load of it, and that will be our self weight. So the total load on soil comes out to be 880 kilonewton. So this will be our first step, that will be finding the size of footing, and for that we'll be requiring the total load on soil, and then we'll be finding the area of footing. So the equation for that will be the total load divided by soil bearing capacity. As the soil bearing capacity is given in the question to be 120 kilonewton per meter square, we are getting an answer 7.33 meter square. So now there will be two conditions in this. First, it will be either will be providing a rectangular footing or either will be providing a square footing. And as it is given in the question that we are designing a square footing, we'll be just taking a square root of this answer. If it was given to be designed as a rectangular footing, then we always will be using the equation. That is, we'll be always taking d equal to 1.5b. If it is not given in the question, then we'll be always taking this relation, that is d equal to 1.5b, and then we'll be finding the parameters. Clear? Or vice versa, you can opt for d equal to 1.5d. Any of the cases will be valid. So now as it is given in the question that it is a square footing, we'll be finding the size of footing, and the size of footing comes out to be 2.70 meter. And now we have provided a square footing of size 2.70 cross 2.70, and the area that we have provided is 7.30 meters square. So this was regarding our size of footing, and the next thing will be to find the net upper pressure. So the net upper pressure, that is our stress. So the equation for stress will be load upon area. So here total load on column will be considering it to be now the factored load. For designing or for finding the size of footing, only the working loads will be considered. For rest of the loads or for rest of the moment calculation, we always will be taking the factored load for it. So now we'll be multiplying the load that is given in the question to be into 1.5, and we have provided the area of footing to be 2.7 cross 2.7. So the value here comes out to be 164.61 kilonewton per meter square. So this will be a plan of the image that we'll be looking upon. So this will be our total area of the cross section. That is, two faces are being given of 2.7 cross 2.7 meter, and this is the column portion in the center of it. Column is of 400 mm cross 400 mm as it is mentioned in the question itself. Clear? So the next thing will be, or the next step will be to find the value of bending moment, and for that we will be finding the total or the load. So the UDL in this case can be obtained from this equation, that is P into BF. P will be a net upper pressure and BF will be the width of the footing that will be taking, as it is a square section, so it will be 2.7 on both sides. So multiplying it by 2.7, we will be getting an answer to be 444.45 kilonewton per meter. And now to find the value of bending moment, we always need to find the critical section, and critical section is always taken at the face of the column. That means if we look at this figure was our top view, or you can say plan of the section, and this will be our critical axis that will be looking upon. You can take this axis on any of the face of the column. Either you can take on this face, either you can take on this face, or you can take on this face. Clear? On any one face of the column you can take this axis. So now we will be finding the value of our width. So as you can see, the total is 2700. This is 400 mm, so the half portion of it will be 200. Total is 2700, so this half length will be 1350, and this was 200 mm, so the remaining length comes out to be 1150. So we'll be finding the bending moment on this case. And now as we are dealing with a foundation, foundation always need to resist the load of the column, which will be acting as a cantilever. Keep in mind. Clear? So now the equation for bending moment will be, considering it to be a cantilever, will be WL square by 2, and the length will be finding this, that is according to our critical section. So the length of our section will be considering this, that is 1150 mm, or you can say 1.15 meter. So the bending moment calculated is 293.86 kilonewton into meter. So the next step will be to find the depth of footing, and to find the depth of footing we will be using the equation for MU limb. Clear? Now as it is a design problem, we always need to assume. So here we will be assuming that it is a balance section. So for balance section, MU will always be equal to MU limb, and as it is given in the question that we are dealing with mild steel, the equation will be 0.18 FCK BD square. So we'll be substituting the value of MU here. FCK is given in the question to be M20. Our D value will be the width of section, that was 2700, and we'll be finding the value of D. So here D comes out to be 191.76. Now keep in mind, for every footing problem you design, you always need to take value that is greater than this value. That means we are getting the value of D to be somewhere around 150 or around 200. For design purposes, you always need to multiply this value either by 2 or 2.5. That means we'll be taking the value of D to be 2 or 2.5 times higher than the value that we obtained. Clear? So here we'll be providing the value of D, that is our effective depth, to be 500 mm. In every case, if you provide the value to be 500, then it is well and good. But just you need to remember, don't put this value directly, because it will be failing under the checks that we'll be dealing upon. Clear? So we'll be taking the value of D to be 500 mm. This was our effective depth. So now we'll be finding our overall depth. So the overall depth can be found from this equation. Now keep in mind, it is similar to a slab problem. Clear? So for two-way slab, as we designed the overall depth, the same phenomenon will be applicable in this case too, because the reinforcements placing will be kept in both directions. That is, we'll be placing along the x-axis too and along the y-axis too. So the final answer will be 500 plus 5 by 2 plus 5 plus the clear cover. We'll be always assuming the clear cover to be 50 in the case of our foundation. Clear? So the final answer comes out to be 565 mm. So the capital D, that is our overall depth, comes out to be 565 mm, and our effective depth comes out to be 500 mm. And the next step will be to provide the reinforcement. So for reinforcement, again we'll be providing the same criteria that we have dealt with the entire RCC portion. The first thing that we'll be finding is the value of PT, and PT can be obtained from the same equation, that is 50 FCK by F5, 1 minus under root 1 minus 4.6 MU upon FCK BD square. So solving it, we are getting the value of PT to be 0.207. And now we'll be finding the value of AST, that will be PT BD by 100. So this value comes out to be 2794 mm square. And for this we'll be providing the bars. We'll be taking the bars of 16 mm diameter. You can either opt for 16 or 20, it is up to you. But always select the bars to be in the range of 16 or 20, clear? And in the previous finding, that was when we found out the overall depth, we assumed the bar diameter to be 10, but for actual design purpose we won't be opting for 10, we'll be opting for higher purpose also, and that's why we have taken the effective depth, which was 191, we have taken it up to 500 to get these checks verified. Clear? So now we'll be providing this section, and the next thing will be to check for cracking. So to check for cracking, we always will finding the center to center distance between the end bars. So as you can see that total 14 numbers of bars are there, so there will be 13 spacings in between them. So this will be our effective length ratio. So this can be obtained from the value, that is 2700 or 2.7 meter was the width of the section, and we need to provide this 14 numbers of bar equally among the width. So 2700 minus 100. Minus 100 is for the clear cover on both sides. We have taken clear cover to be 50, so deducting 50 on both sides will be minus 100, and as it is a clear cover, we need to deduct the half of the bar too. Clear? So as we have taken 16 mm diameter bars, so half of 16 will be deducted on the left side and half of the 16 will be deducted on the right side. So the final answer here comes out to be 198.76. That means we provided a spacing of 198.76. Now we need to check that what is the maximum applicable spacing as per our IS code. So for that we need to move on to page number 46 of your IS code, that is IS 456, and you will be getting the table here, that is table number 15. It is for clear distance between bars. So now as it is percentage distribution or from section considered, clear? Here for this semester we will be always considering it to be 0. And for FY, it is mentioned in the question that we are taking FE for 250 steel, that is mild steel. So for that, the maximum spacing that we can provide is 300. So we have provided a spacing of 198. You can keep this value, or for safety reasons, again you need to deduct 1 bar from it. Clear? It is just for safety reasons. If you directly kept this value, then also it will be okay. So as it is less than 300, our check is verified. And now we'll be proceeding to our checks. And the first check will be check for one-way shear. Now these checks are to be completed or are to be done only if it is asked in the question. Keep in mind here. So for check for one-way shear, the first thing we'll be looking upon is the section. So this was the plan view that we'll be dealing upon. Now you need to remember that we'll be doing checks for two major cases. The first will be check for one-way shear and the second will be check for two-way shear. As the name itself suggests, that the shear will be occurring only on one side, that is one-way shear, either on the x-axis or on the y-axis. So for that you need to plot a critical section. So critical section for our one-way shear will always be plotted along this line, and this line, that is our axis line, will always be taking at the distance of our effective depth from the column face. So this line can be opted on any direction, but it should always be placed at the distance of our effective depth from the column face. Clear? So now we need to find the length of the remaining portion. So the length of the remaining portion will be here 650, as this was 1350, this was 200, and this is our 500. So 1350 minus 700 gives us the value, that is 650. Clear? So now as you can see, this is a hatch portion. We will be doing our one-way shear only along this hatch portion. We will be taking this area for the one-way shear, and the equation for it will be that we will be finding the view, that is shear force on this hatch area. So the shear force will be here P, that was our upper pressure multiplied by hatched area. So the pressure was 164.61 and multiplied by hatch area, that means the area. Here the width is 650, or you can say length is 650, and this was our 2.7 meter. So 2.7 into 0.65 gives us the area. So the shear force in this case comes out to be 288.90. Now we'll be checking for shear, and check for shear will be similar as we saw in the beam portion as well as in the slab portion. So we need to find the value of tau v. And tau v can be obtained from this clause, that is clause 40.1 of your IS code, and it is equation given by VU by BD. We'll be substituting this shear force here, and we are getting the value of tau v to be 0.214 Newton per mm square. Now the next step will be to find the value of tau c. So tau c can be obtained from the value of PT. So PT here it comes out to be 0.208, and from the table given in the next page, you can obtain the value of tau c, that comes out to be 0.326. So as we can say that, or we can prove that the tau v value is less than tau c, so our check for shear or check for one-way shear is completed. The final answer should always be that tau v should be less than tau c. If tau e comes out to be greater than tau c, then the section you have opted for, the dimensions you have opted for is incorrect. You need to change those sections. Clear? So the next thing will be to check for two-way shear. So for checking two-way shear, again we'll be looking at the plan section that we saw. But in the previous check, we took the H area only across one face because it was for one-way shear. Now we'll be dealing with both the axes. So we'll be plotting a rectangle around it. Clear? Now again, the dimension that used to be left is again D. But as the previous case was for one-way shear, we kept the distance apart was D equal to 500 from one axis, and now we'll be keeping it from both the axes. That means this distance and this distance combinedly should be 500. And similarly, this distance and this distance combinedly should be 500. So this individual distances that has to be kept from the column face should be d by 2. Clear? So this will be a d by 2 and d by 2 distances that will be keeping apart, and then will be forming a rectangle, or you can say a square across this. And this will be our b dash that will be looking upon. Clear? So this width will be considering it to be b dash, and this will be the H area that will be looking upon to find the value of shear force. So shear force here will be considering the our periphery. So the periphery in this case will be the summation of all the four sides. So as we have taken one side to be b dash, so the value of b0, that is the periphery value, will be 4 into b dash. So first we need to find the value of b dash, and b dash, as you can see, is the combination of this length. So this length is 400. We have added b by 2 across this length and b by 2 across this length. So this will be 250 and this will be 250. So our length or the periphery on one side or the length on one side will be 900. So total our rectangle comprises of 4 lines. So summation of 4 lines will be giving us the answer, that is 3600 mm. So this entire periphery will be 3600 mm. That is will be referring to B0. So now we'll be finding the value of our H area, that is shear force. So shear force, again the equation will be the same, P into H area. So we need to find the area of the H. So we'll be deducting the inner rectangle from the outer rectangle to find the area. So the area here comes out to be 2.7, that is our outer rectangle, minus that will be deducting from the lower, or you can say the inner rectangle. So the VU in this case comes out to be 1066.67 kilonewton. Now again the steps will be the same. We will be finding the value of tau v, and tau v can be obtained from this equation, but here keep in mind, in respective of b that we used earlier, here we will be substituting the term b0, or you can say bo. That is the only change regarding our one-way shear and two-way shear. So here we will be substituting the length to be 3600. So here the answer comes out to be 0.592, and then we'll be calculating the value of tau c. For two-way shear, you always need to look upon this, that is, this upper portion is given on page number 58 of your IS code, and this lower portion is given on your page number 59. So from this we can say that we need to find the value of Ks into tau c, that is a tau c dash. So when shear reinforcement is not provided, because we are not providing shear reinforcement in our foundation, we always will be providing shear reinforcement only in beams. Clear? In foundation there won't be provided any shear reinforcement. So this is for our foundation, or you can say footing. So in this case it is said that the calculated shear stress at critical section shall not exceed Ks tau c. That means tau v should not exceed Ks tau c. That will be referring to tau c dash. So Ks will be always taking the value to be 1. For square column, keep in mind the value of Ks will be always substituting to be 1. And tau c can be obtained from this case. That is, for limit state method, we will be taking the value of tau c to be 0.25 into root FCK. And for working stress method, that will be not dealing with in this semester. So we'll be always focusing on this value, that is tau c will be equal to 0.25 into root FCK. So the answer here comes out to 1.11, and Ks into tau c again comes out to 1.11. So tau v is less than tau c dash. So our check for two-way shear is completed. Now we'll be moving towards our last check, that is load transfer from column to our footing. That can be obtained from page number 34.4. Here only minor equation is being given. The rest cases to be understood by you. So here the allowable bearing stress. This equation is mentioned here, that in the last line it is said, for limit state method of design, the permissible bearing stress shall be, that means the maximum allowable bearing stress should be 0.45 into FCK. So FCK is given in the question to be 20. So the allowable stress here comes out to be 9 Newton per mm square. And then we'll be finding the force. So as force equal to stress into area, the same equation is being used. So stress was 9 and area will be the area of column, because we are dealing with load transfer from column to footing. So we'll be taking the area of column. So the area of column was 400 cross 400 as it is mentioned in our question. So the final answer here comes out to be 1440 kilonewton. That means it can transfer up to 1440 kilonewton load. That means the column can transfer the load up to 1440 kilonewton. But as the factored load here in the question comes out to be 1200, so the transfer load phenomenon can be sufficiently valid using this case. Is clear? So this was our sum pertaining to our isolated foundation. Solve it because it is important, and again keep in mind checks are to be done only when it is asked in the question. And this is our exercise problem of this session. Do solve it because isolated problems are generally being asked in the examination regarding a square footing. Yeah? So this was our section pertaining to our foundation. So this was our RCC portion that we have completed now. Yeah? Thank you.